really fundamentally, in terms of what's out there, your engine hasn't changed very much in over 100 years. For a piston engine, we can look to textbooks, and for what we're doing, we're kind of writing the textbooks as we go.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about building a better mechanical engine. It's been tried countless times, but in the last 100 years, there's been practically no viable challenger to the piston engine. My guest believes they have the answer. It's a new twist on a design commonly known as the rotary, or Wankel engine. Some rotary engines were used in Mazda sports cars up until recently, but even they had clear limitations over piston engines. Over a decade of experimentation, my guest settled on a design that is smaller, simpler, and stronger than both the piston engine and the Wankels that have come before it. They can build engines as small as your smartphone and big enough for several hundred horsepower. You could find one in your lawnmower or on an airplane. My guest says the size and efficiency are key. In a world where battery EVs are the future, full stop, they believe they can serve as a great complement. He believes all battery EVs are not the answer. My previous episode explained how many natural resources we were using for those. But a smart hybrid with fewer batteries and a hyper-efficient engine may lead to a future that is both cleaner and relies on fewer natural resources. It's this mission to develop a more efficient mechanical engine that could be a true path forward for sustainable energy. My guest today is Alex Skolnick, founder and CEO of LiquidPiston, a mechanical engine developer based in Bloomfield, Connecticut. Alex's father, Nikolay, conceived of this cycle back in 2003, and Alex says the initial design was literally a liquid piston, gas acting on a body of liquid with no pistons for the motor. Alex began working with his father while finishing up his PhD at MIT and joined the company in 2011. We spoke extensively about the benefits of a more efficient engine, which is one of the reasons why LiquidPiston's first customers are the Department of Defense. We also discussed the competition from EVs, both commercially and in the minds of many out there who think that mechanical engines that run on fuel is old news. And I had a little fun digging into what we might find scampering the halls of MIT. I hope you enjoy my conversation with Alex Skolnick. We're here with Alex Skolnick, founder and CEO of LiquidPiston. And Alec, the engine in your car is essentially the same configuration as in one from 100 years ago. How is your engine different?
Yeah, that's a great question. LiquidPiston, we've reimagined the engine from the basic fundamental principles of how it operates, and that goes back to the principles of the thermodynamic cycle. So we started by envisioning a new optimized thermodynamic cycle and rethinking the entire engine as we know it, and the result is a new kind of rotary engine that's smaller, lighter, and more efficient.
And when we say rotary engine, I think some people are thinking of prop engines from airplanes. I think there also was some sort of version of a rotary engine that Mazda might have made. How is this different from those things?
Right. There's these two historical uses of the term rotary engine. So World War II, and in that era, you had the kind of rotary piston engines. But more recently, since the 60s, we had the Wankel rotary engine, which was probably made most famous by Mazda as it was in its sports cars up until recently. The Mazda rotary, it's very well known. It's a simple engine, has just a few moving parts similar to ours, very low vibration, very responsive. It's really an engineering marvel, but it also had some challenges with sealing, cooling, lubrication, efficiency, emissions, durability, kind of everything we care about the engine doing. It kind of struggled with, but it did have very high power density, and it's a very responsive engine, which makes for a fun sports car. But in recent years, they had trouble meeting emissions and durability requirements at the same time. Our approach is quite different. And again, we kind of started with a new thermodynamic cycle and rethought the engine from starting with the cycle. It's like a new operating system for the engine. And when we do that, we turned the old Wankel rotary inside out. If your listeners are familiar with the Wankel, that engine has a triangular rotor inside of like a peanut-shaped housing. Our engine's the exact opposite. It's got a peanut-shaped rotor in a tri-lobed housing. And so basically, it's a very different implementation of the rotary, and it solved all those challenges while operating on this new cycle.
Yeah, that's how it was explained to me when I started talking to your team, was essentially it's a motor that's inside out, right?
Yep, an inside out Wankel. Yep.
Yeah. Other than this rotary engine that Mazda was doing, have there been efforts to use alternatives to the engine in the past? I mean, true alternatives to the engine that we've known for the last 100 and so years.
Piston engines have been around for a very long time, and sometimes we joke that 10 or 15% of the world's patents are for new engines. But really, fundamentally, in terms of what's out there, your engine hasn't changed very much in over 100 years. These engines have been incrementally improving, but there's been very few fundamental disruptions in technology, and everyone's been trying to do something else, fuel cells, things like that. But the piston engine has been very hard to beat.
Yeah, what you're thinking is this is really the first viable mechanical alternative, right?
Right. So our engine's very simple. It has just two moving parts. It can be up to 30% more efficient than a gasoline engine. It can be up to 3 times more fuel efficient than a small turbine. So that opens up a whole new avenue of applications as well. And we're about 10 times smaller and lighter than a diesel engine. So today, diesel engines, they have some of the highest efficiencies in terms of combustion engines, but they're really big and heavy. And that makes them less useful in applications like hybrid applications, for example. You really don't see a lot of hybrid cars that run with diesel engines, even though those engines are a lot more efficient. And the reason for that is because the electric side and the battery is already quite big and heavy, and combining that with a diesel engine would be just overly burdensome on a vehicle. But with our engine being extremely small, 10 times smaller than a regular diesel, and bringing the efficiency of a diesel to something like a car, we can make something like that viable.
So if it's that much smaller, Alec, you could put a 10 times smaller engine in a diesel truck.
Yeah, you could either use a smaller engine, or you could get more power for the same size, or you have enough space and room now to hybridize your system, right? We can leverage what's good about electrification and also still have the engine in there.
Right. You could still then have all the parts that connect to the engine to give it the torque, right? It's not so small that that is compromised. Does that make sense?
Right. On a torque side, we're about 3 times smaller and lighter for a comparable torque piston diesel engine. On a power side, we can run significantly faster than a regular piston engine. We don't have oscillating pistons and valve trains. Our engine is ported. It likes to go at high speed. With that, the engine has no problem running at very high speed, so you get a lot more power out of it with the speed. But in terms of comparing to a diesel, which usually runs pretty slow, we're about 3 times smaller and lighter.
Yeah. So this is Energy Cast. Tell us what you think this means for the energy sector.
Well, there's a lot of challenges today, as we know, in the energy sector. If you look at the world trying to go with EVs, for example, it's working okay as EVs are just a few % of our solutions for mobility today. But projecting out into the future, we're already having some challenges now. And if you look at some of the recent projections that came out, where in 2040, we're trying to go 80% electric in light duty vehicles, that requires a 40x increase in lithium and nickel, and a 20x increase in copper, graphite, and cobalt compared to 2020 levels. Just tremendous resources required to go electric. A lot of people don't really consider the holistic system of going electric, right? So if you think about it, we're told that an electric car may have 0 emissions, and that's physically true for the car itself. There's no tailpipe, but really what we've done is kind of moved the emissions off the car and put it somewhere else. These vehicles take a lot of energy to produce, and also you have to charge the battery wherever you go. So where do we get all that electricity from? There's not enough electricity in the country if we're going to just overnight switch to a fully electric vehicle setup. These are all challenges that we can help address, and we are big proponents of vehicle electrification. One of the great things about going electric with a car is it takes a lot of energy to accelerate your vehicle. That's where a lot of your fuel goes. The nice thing about electric is that you can put a lot of that energy back into your battery when you brake, right? Regenerative braking. And that's really what makes electric vehicles extremely efficient. Now, the challenge with electric, it's not really so much the electric side itself, it's really the battery. Today, there's about 100x gap between the energy density of the best battery technologies and that of fuel, right? That's a huge gap. That means that something like a Tesla or a large EV sedan would be carrying more than 1,000 pounds of battery. And that's a lot of dead weight that you're carrying there. And that in and of itself is not efficient. And then it has all the challenges of its production, and then environmental challenges also in recycling and dealing with batteries when they die. All of these are challenges that we can help address with our technology.
That's a great point you brought. I mean, all great points. It just so happens that my last guest that I interviewed was a mining company. They were opening new mines, and the statistic that they gave me, you mentioned copper, was that it's going to take something like 28 of the largest copper mine, which is called Escondida, to fulfill our green energy needs as we've defined them at this point. Those mines don't exist, right? There's only one of them. I think there's now going to be a more emerging conversation about, yes, we want carbon free, but we also need to be lean on our natural resources.
Right. So there's the natural resources, and there's also power generation. If you look at how much energy is pumped out of a fuel station, like a gas station, and you divide that by time, energy divided by time is power. And if you want to displace 4 gas stations like you might have at a busy intersection, you would need a small nuclear power plant to generate the same amount of electricity as what is pumped through several gas stations like that. These are really kind of hard considerations. And when you look even broader on the global scale, we're finding that clean energy is something that we would like to have, but there are practical limitations to it as well, right? We need to be very careful how the supply chain is structured. You can see in the conflict with Ukraine, for example, with Russia holding a lot of power because of its importance in the supply chain of fossil fuels in that region. We need to diversify our energy portfolio. And that's a matter of national security. It's a matter of if a supply chain gets disrupted, that you still have another way to turn. So we really don't want to put all of our eggs into one basket. And the more that we can distribute our energy generation, our energy storage, the better, in our opinion.
Alec, does this become a non-starter a lot of times when you're trying to say, hey, I've got an engine, it's extremely efficient, it's not going to use the raw materials? Do you get a lot of people kind of in the modern headspace that are just saying to you, well, we're done with that. We're done with a carbon-based fuel and we're EV now, right?
There is a fair amount of that. And unfortunately, people have been kind of convinced that battery EVs are zero emission and have zero carbon footprint. And that's quite far from the truth when you really look on a well-to-wheel basis. And it's a whole ecosystem that's required to support an EV. And the whole system needs to be taken holistically. We're not advocating an engine-only solution. Our opinion is that the world should go hybrid. A hybrid solution means you can use smaller, lighter, cheaper batteries and still keep all the other benefits of electrification, including the efficiency gains that can provide. And maybe your car will get 30 or 40 miles of range instead of 300 miles of all electric range. So it'll still cover 95% of your daily driving needs. And then you just use the engine for those cases when you need to have the longer range. But going hybrid gives you a lot more knobs to optimize from a overall standpoint, just looking at the EV as a component of an overall system.
Right. And I think there's also some survey bias based on where you live. And you're in Connecticut. I'm in Charlotte in the middle of the city. And if you ask a lot of these people how many electric vehicles are on the road as a proportion of cars, it's 20, 30%, it's half of a percent, right?
Right.
And I think that there's going to have to be a little bit of everything here.
Yeah, we agree.
So it doesn't have to be gasoline, right? It can be other alternatives. I think someone had mentioned hydrogen, biofuels, hydrogen. What can this engine run on?
The really cool thing about our engine is that we've demonstrated it on a variety of different types of fuels, gasoline, kerosene, jet fuels, diesel fuels, and recently we've run some gaseous fuels like propane and hydrogen. Hydrogen is a really interesting fuel for us and kind of a long-term potential to take engines actually back into a zero emission framework. Hydrogen can be produced by splitting water using electricity, so you can use solar energy or other renewable energy to create hydrogen. And then inside an engine, you basically recombine the hydrogen with oxygen, and the output from your tailpipe is primarily water. The challenge with hydrogen is that it's extremely volatile and explosive. For piston engines that have hot spots like exhaust valves, it really doesn't work very well. But rotary engines have been known to work better on it. There's fewer hot spots. And when we tried it, we were able to get it to work with just a few weeks of adjustments.
That's all right. So how much more efficient is this engine? You mentioned how much smaller it is, and maybe you've said this, but how much more efficient is it than a typical piston engine?
Right now, early on, we're targeting efficiencies similar to that of a diesel engine, which would be about 30% more efficient than a gasoline engine. But long term, we want to be even more efficient than a diesel engine.
I think the big question people might be wondering is car companies spend billions of dollars on R&D every year, and there's many car companies. Why did we not see an innovation like this from them?
That's really a great question. And the car companies have done a great job in making incremental changes to engines. And, if you look back over the 100 years, engines have certainly improved dramatically and achieved some pretty remarkable things. But really, nobody has gone back to the basics, the fundamentals of how engines operate, the physics of the engine. And that's where we're starting. My father's a PhD in physics. My background's in modeling and optimization. So we kind of came at it from outside of the field and really just started with, hey, what does physics say should be possible? And how do you optimize from a physics perspective? And then we look at, hey, okay, this is how an engine should operate on paper. How do we implement that in reality and metal? So for us, it's been kind of a two-step process, but it's really a fundamental breakthrough and not an incremental change like what the car companies have been doing.
Sure. I want to ask a little bit about you. Went to MIT and then have been doing LiquidPiston for the last 12, 13 years at this point. When you were at MIT, that wasn't your focus on building engines like this, right? It says it was robotics.
Yes. So I have a PhD from the computer science lab at MIT with a focus in robotics and motion planning and optimization. We started the company. I was helping my father. My father was a innovation consultant, and he was kind of focusing on clean energy systems. He's got lots of patents in fuel cells and batteries and things like that. And when I started at MIT, I got hooked up with some of the business school students, and we ended up entering into a competition called the MIT 50K. And we won second place out of about 150 teams coming out of MIT. And that's kind of what launched the company. So while I was doing my PhD, I was kind of helping my father out with the company. And as I finished up my PhD and was doing a postdoc, I decided to join the company full time.
So MIT, I think a lot of things come to mind when you think of it. What would we be surprised to see if we walk the halls of MIT? I'm just imagining the future happening in a place like that.
Well, MIT is a really remarkable place, and it's full of exceptionally bright people. We had robots everywhere in our lab, and, walking robots, flying, crawling, anything you can imagine. And, interestingly, I think in my lab, out of about 20 people, there were probably only about 2 that did not have a startup company. It's kind of ingrained in the culture there to really innovate on cool new things, and startups are just kind of part of the culture. It's a really neat place, neat environment.
You were obviously in robotics, so you probably spent a lot of time that end of the hall. Were they focusing on a lot of energy-related technology?
My group was focusing on under-actuated systems. That's just fancy speak for having fewer motors or fewer degrees of control than the system has physically. For example, walking robots. But power and energy was critical there too. I was working on the little dog robot at MIT, and that's the little brother of the big dog. Some of you might be familiar with the company Boston Dynamics, which makes these really amazing robotic platforms. So we were working closely with Boston Dynamics and with DARPA. And actually, my friends at Boston Dynamics helped introduce us to DARPA and helped get our first funding. Power and energy has always been a big issue there. And as robotics have gone electric, they're going to need power and energy as well. Batteries have also come a long way in the last 20 years. They're doing a lot of remarkable things with batteries today too.
Take us through the last, decade or so. What has been going on at LiquidPiston? It sounds to me like this is just one of these endeavors that is going to take a lot of years and work before you have a product that goes commercial. How did you keep your head up while you're doing all this work on something like that?
Yeah, people think that it may be easy to develop an engine, but really there's a tremendous amount that goes into developing a new type of engine. For a piston engine, we can look to textbooks, and there's a lot of empirical guidelines, a lot of knowledge that goes into that. For what we're doing, we're kind of starting from scratch and writing the textbooks as we go. When we first started out, it's really been all about the cycle, right? We're trying to prove out this new cycle, and we've experimented with a large number of different types of engines trying to pursue the cycle. So what we're developing now is called the X engine. This is our 5th generation of the engine architecture. We're kind of adapting the engine so that it can run on this new cycle. And this is the one that we're going to take to the market. So each one has gotten us closer and closer to the point where we're really demonstrating these remarkable breakthroughs here, but it is taking some time.
Yeah. And so finally, we're getting to the point where we're getting dollars and we're getting contracts, right? You received awards from DARPA, the Army, the Air Force. What do they want to see demonstrated?
The question is not only technical viability, but also commercial viability. There have been a lot of startups that have tried to introduce a new type of engine, and many of them have failed on a commercial basis. And most of them try to go straight into the automotive sector, which is a very conservative sector to go into. We've taken a bit of a different tack, and we found a very immediate and painful need within the DoD for our technology. The DoD is the single largest consumer of oil on the planet. For them, everything's about logistics and efficiency, and power and energy are critical to basically everything that they do. The Army is very mobile. They need to get power to the front line. It can take up to 100 gallons to push 1 gallon of fuel to the front line. And that's not only expensive, right? It can be $400 or $500 to push a gallon to the front line, but it's quite literally measured in lives, because recent conflicts in Iraq and Afghanistan, half of our casualties were in supporting fuel and water logistics. These convoys of fuel make really great targets for the enemy. And then because the military operates primarily on jet fuel, they want everything to run on jet fuel, which means that the engines that they use, they're all basically diesel engines, which are really big and heavy. The reason it takes 100 gallons to push one to the front line is because everything kind of multiplies, right? If you have a large generator that's going to the front line, well, you need a truck to move that generator, and then you need a big aircraft to deliver that truck, and it cascades from there. So by making power and energy solutions significantly smaller and lighter, like a 10x reduction in size and weight, that's a game changer for the DoD. And because of that, they're willing to make pretty significant investments into this. We just announced a $9 million contract with the Army. Over the coming months, we're going to be announcing more about what we're really kind of doing with the Army. So that'll be news that's coming, but it's all basically focused on mobility and power generation for the DoD. And we're really excited to support the Army, and they're a fantastic first customer for us. And then we think that this is going to be the first domino, right? So rather than going into the automotive world directly, we're starting by helping out our friends at the DoD, solving their immediate problem that they have, and then the dominoes can fall from there.
Yeah. So you ultimately would like to be behind the badge of a Chevrolet, for instance, right?
Yeah. The engine is scalable. You can use it in handheld tools, and it can scale up into the hundreds of horsepower. And we're trying to make an engine that's better on virtually all parameters. So anywhere that you see engines today, and also even small turbines, we can be competitive with a small turbine, but with much better efficiency. So really anywhere that we see engines and small turbines, we can be competitive.
All right. Alex Skolnick, LiquidPiston, thank you so much for your time.
Yeah, it was a pleasure to be here today. Thank you.
That was Alex Skolnick, founder and CEO of LiquidPiston, a mechanical engine developer based in Connecticut. I want to thank Alec for his time, as well as Emily Meyer at Communication Strategy Group for setting this up. You can find plenty of pictures for this episode on energy-cast.com, as well as on Instagram at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 154. Be sure to join us next week when you meet the nuclear company that's had Hollywood come calling twice. Until then, I'm Jay Downhauer. We'll see you next time.